We're back for more exciting, attractive fun. Hendrik Lorentz, cool dude, 1853 to 1928, realized that you could create forces between things if there are differential charges between objects. In other words, you could have two objects spaced apart, and if I can create a potential between them, for example, one is grounded and the other is at a potential of 10 volts, the force between them will get greater as an inverse square of the distance where they'll snap together. You can have a coil in a permanent magnetic field that also creates a force. So I can have a permanent magnet and then a coil of wire, and it'll cause motion. It'll cause a force which will cause motion. This is a Lorentz force actuator. Now there's some of you rockers out there who are like, oh, big deal, man. You know, I'm going to like go out and play my electric guitar. Twang. But we should all be singing this song of love for Dr. Lorentz for discovering this and quantifying it and writing the theory behind it so you can design things that do what you want them to do with respect to making these types of actuators. So for example, this structure here was for an electrostatic actuator to actuate a microsilicon relay, where this structure here, this distance was 0.2 millimeters across, or only about 8,000th of an inch, for a little electrostatic relay that could switch household power. This is from a rock and roll concert. Ah! Really loud. Which is made possible by speakers. Speakers are often called voice coil actuators because it makes your voice amplified. So I could sing, which I won't, because we don't want to shatter the lenses, into a microphone, which would cause vibration of a diaphragm. That vibrating diaphragm in a permanent magnetic field would induce a current in the coils, which would be taken back and through the electronics amplified. That voltage sent out to the coils on a speaker, which would then cause the speaker head to move in and out and cause the air to move in front of it, hence hearing my voice again. So let me connect up this speaker and let's see what happens. Do I have a little power supply? See, you all didn't know I was a rock and roll star. Listen. Similar sound, right? Actually, I'm a big rock fan. Actually, I like all music. Depends what mood I'm in. Right now, I'm in kind of an actuational mood. What we've done here, see, that's a speaker. What is all this stuff? Well, what this thingy is here is, it's actually a project my son had where he designed this bistable toothbrush where if you push too hard when you're brushing your teeth, this little structure here snaps through. So we'll talk about that. Hear that? You push too hard, it lets you know. We'll talk about that when we go into structures and fun with nonlinear structures and hinges and things. But he had to test it to see when you were brushing, does it affect when this force releases or not? Because if you brush faster, will it change the force at which you're applying to your gums? So he hooked it up with this audio speaker because he needed a cheap system to cause motion. Now this is just a static power supply, but if you had a programmable power supply, you could put in a sine wave and make this thing go. But right now I'll be the mechanical sine wave. I love you, baby, yeah, yeah, yeah. Now this is very low frequency, so only the whales out in the ocean here are starting to dance to this. But imagine, so you see, I can use this Lorentz force actuator, which is what drives the speaker, as an actual actuator to drive this system. And notice, by the way, how we're using one of these folded flexures we talked about earlier in the linkage discussion, topic 4. That's a flinkage. And notice that it's a double flexure. So the parasitic error motions that you get in a 4-bar linkage are canceled by using 2 of them. We talked about that. That was in the slide. You remember there was this purple flexure up here in the corner. Now I know what some of y'all are thinking. Man, here he goes again. Whoop! Oh look, shiny thing. Off on a tangent again. Can't he just talk about one thing? No. Because we are designers. And designers' heads are like pinball machines. Bing, 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 bing. And when you're thinking about anything, you should instantly be thinking about everything and looking for patterns that match. Okay? So when I talk about, oh my goodness, see what happens? C-3PO lost his chains. He's broken free of his chains. He's a true designer. When you're looking at one thing, for example, actuators, you want to always be cycling through your entire system, looking for the parasitic motions, looking for, if I fix this, what else may break? That's the beauty of being a design person. You're allowed and encouraged to think about everything at once. And if you don't like to do that, you just like to focus on one thing only, and I don't want to be bothered by everything else. That's also excellent. Because remember, most of design is about teamwork. And on a team, you're going to need people to think about everything at once. Say, oh my goodness, this is going to be a problem. Let's get someone who can really focus on just that problem and really do it. Okay? So there's a fantastic thing in the world of design and engineering is everybody can have lots of fun. All right? So we showed how a Lorentz force actuator, what it can do, how they're used, how you have fun with them. And also demonstrating here, which a little bit of work in the carpentry shop, you can put together some very effective types of machines and instruments just with stuff you find lying around. Okay? You don't need a $10,000 voice coil actuator. You can go and get a cheap speaker and put one together pretty easily. Where else are these actuators used? Well, if these weren't used everywhere they are, we would have no cell phones. Why? Because the chips inside this cell phone are made in the semiconductor process, which uses a machine called a wafer stepper. Wafer steppers use these little fine motion positioning stages that position the silicon wafers under the lens stack, which then imprints the pattern from which makes that wonderful magic circuitry that gives us the cell phones. The magic of a cell phone traces itself back to the actuators that were designed because of this dude, Hendrik, and all the other fun people we talked about, and all the bearings and everything. The entire world is based on fun with engineering. Okay? And you got to have good business, and you got to have the lawyers to protect your stuff. You got to have a system that works together. This system design. Okay? All right.